It is my pleasure to introduce Дэвид Талбот. So he agreed actually to complement my short introduction. Let me even start with some important parts. So David understands Russian, so you can ask him questions in Russian. He will probably try to answer your questions in Russian, but
we'll see.
Okay, a short introduction. So David graduated from the University of Oxford, then he got his PhD from the University of Edinburgh, and he spent roughly 5 years, I believe, at Google working on...
I spent 5 years at Google Translate.
At Google Translate?
Yeah, a few more years at Google, yeah.
And the last but not least thing that I know is that he teaches a class on machine translation at Yandex School of Data Analysis, which is short in Russian. Yeah, please do.
Thanks for that.
You guys enjoy.
Thank you very much for inviting me here. So I'm David. I worked for just over 5 years as a research scientist on Google Translate. My interest started in machine translation when I was a PhD student in Edinburgh, and I focused on machine translation at that point. And this was at the sort of reasonably early days of Google Translate, so wow, almost 10 years ago. I went to Google Translate one summer for an internship, and I had a really interesting time there, so I carried on in that field, finished my PhD, and then went back to Google and worked there for about 5 years. So about 10 years ago was when the data-driven machine translation really started to work. So I mean, by data-driven, I mean both what some people called phrase-based machine translation and what's more recently happening, which is based on neural networks, so neural machine translation. The thing which joins these all together is it's machine translation where the computer learns to translate purely from data. Okay, so there's not really a big role in these systems and in this area for linguistics. We will talk about that a bit more. But okay, so I want to understand, firstly, if you have any questions, please just ask or put your hand up and I will answer questions. Please don't wait if you don't understand something. But so I want to have a bit of a better idea about your backgrounds. So who here is a student of computer science? Okay, so computer science, okay. Is there anybody here who is a student of linguistics? Okay, cool. I studied linguistics before I did computer science, so it's an interesting field. They share a lot in common. And who here has done any studies in machine learning? Okay, so quite a few people. Okay, cool. Okay, and who here doesn't understand me? Okay, that's really cool. Well done. Great, everybody does. So please, I'm not going to speak Russian because my accent is horrible, but I actually understand Russian quite well. I've lived in Russia quite a few years in the past, and it's a beautiful language, and I won't ruin it by trying to speak it. But if you want to ask questions in Russian, it's absolutely fine. When I teach in Shad in Moscow, many of the students ask all their questions to me in Russian, and it's fine. It's just because this is not about English; it's about machine translation. Okay. So let's see if I have a plan of what we're doing today. Oh yeah, okay. Okay, I guess I have to do this thing. Okay. So what we're going to do is we're going to learn about the problems involved with machine translation. Okay, so this is nothing really to do with computer science. It's to do with translation, which is a problem in the real world. And we're also going to learn mostly about how you can build a machine translation system from data. Okay? and how you can improve that system, and how maybe you can use some linguistics to try to improve that system. This is basically what people have been trying to do for at least the last 10, probably 20 years in this area. Okay? And today, so there are two big success stories for machine translation using data. One of them started about maybe 15, maybe even 20 years ago, was phrase-based machine translation. Phrase-based machine translation is something that we will talk about today. It's using bilingual data, so sentences, say, in English and Russian, and learning a model which can translate between phrases, and putting that all together to make a machine translation system. Phrase-based machine translation is what Google Translate started with. It's what Yandex Translate started with and still uses. I mean, at the moment, I guess they're transitioning. And it made machine translation work. Okay, so who here has used Google Translate or Yandex Translate? Okay, okay, yeah, okay. So you all used it, but why did you use it? Yeah, good. Why did you use it? To do your homework?
I have to translate stuff.
You have to translate stuff. Okay, okay. So people have very mixed feelings about these services, because if you speak, I mean, obviously you all speak quite good English, I hope, because you're listening to me. And it means that if you're using a service like Google Translate or Yandex Translate, you very quickly see some very stupid mistakes. Yeah? And you're like, how can it be so stupid? Why does it make that mistake? Okay, so maybe we try to understand a bit about why it can make stupid mistakes. But even if it's easy to find the problems with these systems, on the other hand, they've been very, very successful, and millions of people use them every day. Like literally millions. In fact, probably, yeah, it's hundreds of millions of people use them every day. So they must be good for something. And the main reason that people use them is the phrase-based machine translation. Okay? So we will talk about some things to do with phrase-based machine translation today, and we will try to build a very simple model to do some part of that task. Okay? And then tomorrow, we will move to the more recent research, which is neural machine translation, using neural networks. It's become the state of the art. So the best machine translation systems today are built using neural machine translation. This is only true in really the last 12 months or last 2 years. So 2 years ago, the neural machine translation was starting to work, but it was still not as good as the phrase-based. But now it's quite a lot better. Okay? So we will look at that tomorrow. Okay? So today we're just looking at really at phrase-based machine translation. Okay. Okay. And so today, because we're doing phrase-based machine translation, we're going to focus on some specific problems which actually might be useful outside of machine translation. So hopefully you learn something that isn't just about machine translation, but is useful for statistical modeling in general. Okay, we'll talk about that more a bit later. Let's have a look. Okay. Okay, so first, why is translation difficult? Why is it hard for a computer? I mean, it can be. Does anybody have any suggestions? No?
Because words are not natural for computers.
Yeah. Yeah, words are not natural. Words are not natural for computers. They have many meanings often. So if I say the word, I don't know, if I say the word bank, yeah? What's the Russian for the word bank? I mean, there's quite a few translations, completely different meanings, yeah? It could be a river bank, it could be a financial bank. Okay, so there's ambiguity, and computers don't naturally handle ambiguity. Yeah. What else is difficult, do you think, though? What else is difficult? Let's ask one of the linguists. There's some linguists here. What's the difference between different languages? What can you tell me some way that different languages are different? Obviously, they have different words, but what else do they differ in? Yeah.
Different syntax.
Yeah. They have very different syntax. Different structure, yeah. So they have a different structure. That usually or often means they have a different order for the words. Even if the words mean roughly the same things in English or Japanese, they're completely different order, yeah? And that's actually a very, very difficult thing, yeah? Because when you take, well, let's come to that in a minute. Okay, so the ordering of the words is another very difficult thing. And how about, why, you probably all know, why is Russian difficult for non-Russian speakers to speak?
Because of the way Russian constructs new words.
Yeah,
Suffixes
the suffixes, exactly, yeah. So the morphology particularly. There's so many things which need to agree that if you didn't learn it when you were a child, it's very hard to do it at the right speed. That's why I can listen to Russian quite easily, but I hate speaking. Okay, so let's go through this quickly. Actually, I have one question. We will need to use laptops during this session a few times. So I see that some people have a laptop. Does everybody have a laptop, or are they sitting next to somebody who has a laptop? Yeah? Because if not, we need to maybe arrange people. So I see lots of people don't have a laptop, and it's good that you're not on Facebook while I'm talking, but but do you guys have laptops at the back? Yeah, you do. Okay, cool. Okay, cool. So this is just to go over these things. Yeah. So ambiguity. Finally, a computer that understands you like your mother. I want you to give me 3 completely different translations of this into Russian. 3 completely different translations. 3 translations that mean 3 completely different things. It's very easy for a computer to make these mistakes, but finally a computer that understands you like your mother. So somebody please translate to Russian. Come on.
Наконец-то появился компьютер, который понимает тебя как твоя мать.
Yeah, that sounds like the most natural translation, yeah?
В конце концов, компьютер поймет вас как мать.
Yes. And let's see, I think I had 3. So, yes, that's the most natural translation, yeah, I guess. This is a completely reasonable translation. It's a completely reasonable translation. Why are you laughing? This is completely reasonable. You know that's not the right translation, but it's right. It's totally. How can a computer know that that's not a good translation? Yeah, how? And so this is quite. And this is the last one. This is a little bit different. Yeah, this is the one you gave. Yeah. So this is at least 3 different ones. Actually, if I ask you all to translate this first English sentence, probably you will give me like 50 different translations. It's very possible. Okay, so once a sentence becomes longer, the number of different interpretations increases somewhat fast, sort of exponentially, I guess, in some senses. And it's very easy for you to have a sentence of 100 words which has thousands of different interpretations. And humans are extremely good at just taking the paths in these different interpretations which make sense. We have all our knowledge about the world, we know what the person is likely to be saying, we have the context, we understand the words. We don't see any ambiguity, but the computer, there's no reason that a computer will not make these mistakes. Yeah. Okay. Then the other thing was the word order. So if you speak Japanese, this is basically, as English, not all languages, words in the same order put. This is meant to be how Yoda speaks. So yeah. And this is actually very similar to the way that they make him speak in the English version, at least, is very similar to how the words are organized in Japanese. Okay? In Japanese, you put the verb at the end of the sentence. Yeah? This is the most important thing. Okay? Okay, yeah, so this is just an example of that. So if you sort of see, so this is the colors here are the words which mean the same thing. So he is going at the beginning, the train is going here, so the prepositions like by and to, they go after the words in Japanese, but they go before the words in English or in Russian, and the verb goes over here, yeah? And reordering, in some senses, might be the most difficult problem in machine translation. It's definitely the biggest problem for phrase-based machine translation. Computationally, it's a very big problem. Any idea why reordering of words is a computationally difficult problem? Do you have any ideas?
It's not possible just to replace words.
Yeah, you have to rearrange them. So if you have to rearrange them, if you have n words, yeah, if you don't know what is the right order, and you just have to search this big space of different ways to reorder n words, then it's kind of factorial. Yeah? If you have some information, maybe you know this is the correct reordering. But if you don't understand, if you don't have a model to tell you what order, the a priori, you have n words in English, and you have to find the right order for Japanese. You have to try a huge number of different possibilities. Okay, and in practice, in a phrase-based system, when you have a very long sentence, they cannot consider all the different permutations. It's just too many. Yeah. And many errors. If you look at the errors which a machine translation system makes, often it's to do with reordering. Okay? For example, I guess, yeah, if you look at the Japanese to Russian translation on Yandex Translate, I'm sure you will see some very strange word order. Okay? It's a big problem. It's very, very hard and it's because of the computational side of it. Okay. And then morphology, like we said. So George W. Bush was quite famous in English for not being very good at English. I mean, I shouldn't laugh really, but he quite often made very basic mistakes in English, like this one. Is our children learning? It should be are our children learning? So this is a real quote. But morphology is obviously, and I already mentioned this, you guys speak Russian, so you know it. Without even thinking about it, you know it. But if you look at, here I put some colors to try to indicate things which are agreeing with each other, yeah? So the things which are the same color are in some sense agreeing, yeah? So these are the same case, this is, I guess it's different, but this is agreeing with, this is part of the same construction, then these are there. And the choice there of Bill is dependent on a word that could be like 50 words before. Yeah? So the problem here is really that the information you need to choose the correct word here is all the way back here. So you can't just use a small window and do things locally. If you can translate word for word, then maybe it's not so difficult. But you clearly can't translate word for word because you need to remember when you're translating this word, when you're translating into this word, whether you use this masculine noun or a feminine noun or a plural noun, and it will make a difference, okay? So the agreement is, it's what linguists call a long-range dependency. So dependency, and you have them in English. You can say, he wasn't very sure of himself, or she wasn't very sure of herself. You have it in English, but it's not so obvious and it's not so common. But in Russian, it's huge, and it's really hard. If you look at machine translation, it often makes these mistakes. It usually makes these mistakes, actually. Okay, and then finally, one of the things is that the way that different languages communicate information can be quite different. And I'm not sure if this is very clear in this example, but English has very, very little morphology. We don't have many words where you can look at the word and decide, is it the subject or the object? Yeah? In Russian, most words you can tell by looking at the word, is it the subject or is it an object? Yes? So you can tell that sabaka is a subject. It doesn't matter about the rest of the sentence because it's sabaka and not sabaku. And the same with this. So you have a lot more freedom about which order you put the words in because the word itself has this information. In English, the position of the phrase has this information in a sense. Yeah? So in English, the position of things is much more important than in Russian. Okay? It's a bit of a vague statement, but how do we sort of encode the position of things? It's quite tricky. Okay? Okay. Okay, yes, and this is obvious. I mean, if you're stolen painting, so it's very easy. I'm not sure what Google Translate or Yandex Translate translates for these, but it's very easy to think of funny meanings for these sentences. So, well, this one is stolen painting found by tree. You need to know that a tree is not a living thing, or is not a, what's the word? Is not something that can find things. Otherwise, it could just mean that the stolen painting found by boy. Yeah? It means something completely different. I saw a man with a telescope. This is, I think, one of the most famous sentences for people doing linguistics in America in the 1970s. I saw a man with a telescope. Do you mean that you saw, was he holding a telescope? Or did you see him using your telescope? I guess in Russian it's not ambiguous, yeah? In Russian you have to decide which meaning. In English it's not obvious, but usually people would think you meant using the telescope. Okay? Okay, let's finish that. Okay. Okay, so there's ambiguous words, there's word order, which is this big permutational, this sort of almost factorial space that you need to worry about. There's dependencies between words. There's also the problem that usually when we try to learn models from data, in machine learning, usually you have the input data and you have the output data, and usually there's one correct output. So, for example, if you're trying to recognize digits from handwriting, yeah, you have an image and you have the correct label. Maybe you have this image which is like this, and this should be a number 7, okay? And you have another one, it's like this, and this should be a number 2, okay? So when you trade, this is the image, this is the label. It's very clear. There's no ambiguity. There's no different possibilities. In machine translation, we have an English sentence, yeah? We have an English sentence, and we have, say, a Russian sentence, yeah? But for any English sentence, there could be like 100 different Russian sentences, which are all actually okay, yeah? If this English sentence is 100 words long, there are thousands, probably, of possible good translations. So this is a problem because usually machine learning algorithms want you to produce the output in your training data. Yeah? And if you don't produce that output, then they say you got it wrong. But maybe your system just produced a different good translation. And how do you know? Okay? So this is the problem that there's not a, what's the right word for it? There's not a distinct label for each training example. Okay? And this is, in some senses, the most important thing for our class today. The data is not exactly fully observed. So what I mean by that is, if this is an image and this is the label, yeah? So this is some pixels and this is a label, then in a sense, we have all the information we need. We need to train a classifier that takes the pixels, somehow tells us it's number 7, okay? I haven't actually said this yet, but what data do you think the Google Translate and Yandex Translate are trained on? What data do you think they use?
Books.
They do use some books, yeah, they use some books, but what exactly? So let's be specific. So what are the training examples? Do you have any ideas what they might train?
Corpuses,
Parallel corpuses, yeah? Yeah, exactly. So parallel corpuses. So a parallel corpus is just some text, yeah? Could be a big amount of text. And usually in computational linguistics, in NLP, usually a corpus is split into sentences, okay? So you've got the English sentence, you've got another English sentence, okay? In a parallel text, you also have a Russian sentence, say, okay? And these two go together, okay? So somehow we decided that these two, this is meant to be like, English sentence with the Russian translation, English sentence, Russian translation, okay? Maybe, let me see if I have a picture, wait a sec. Okay, yeah, cool. So, oops, no, but I kind of gave the thing away. Okay. We won't really talk about where the parallel text comes from, but you can find, there's books, you can find web pages which have already been translated. You can take those two texts and you can try to find the sentences which match. Okay, so that isn't such a difficult thing. It's not easy, but it's quite straightforward to do. And then you have a parallel text. Okay, but the problem is your parallel text is just a whole sentence in one language. We'll call it the source language. So here the English is the source language. And you have another sentence in the target language. So you have these different sentences, but you don't really see how the translator went from the one sentence to the other sentence. Yeah. So these sentences might be very long. And here's an example. Yeah. Oh, this is not a long example, but here's an example. This is in French. English and French, okay? And this is, I guess, one of the key, this is from a paper in '93 by these researchers who were actually in IBM. They're definitely in IBM. And they were basically the first people to really try to do data-driven machine translation. And what they said was, because they just have a parallel text with sentences, in order to learn a model to translate, we need to break the translation down into parts. Okay, so here, what they did is they proposed the idea of aligning the words. Okay, so aligning the words. In other words, you have the English sentence, you have the French sentence. That's your training data. Okay. But as part of the training process to train a translation system, they said, let's try to work out which word is corresponding to which word. Okay, so this thing is like an alignment. This thing is an alignment. It basically is one-to-one here, one-to-one here. So there is les, proposal, proposition. These two words in English, you can't really separate them very easily in French. So there's kind of three words. That's a typo, actually. I didn't notice that before. Anyway, will not should be ne seront pas, and now be implemented, or now is separate, that's now there, but implemented and be implemented is this phrase here. So this kind of means put into application. Sort of, it's a slightly different phrase in French. So their idea was actually really groundbreaking, because once you start to break down the training data into alignments at the word level, you can actually start to learn something quite practical. Okay, you can actually start to understand what is the translation of this word proposal. It's probably proposition. Yeah. What's the translation of this phrase will not? It's probably this thing here. Okay, so by having these word alignments, by suggesting that you should first align the words, they really revolutionized the approach. And even though in the new neural machine translation approaches, they don't exactly do word alignment, there is, and we'll see this tomorrow, there is a component in the neural machine translation system which is doing something very like this, okay? So word alignment is, I think it's quite a cool thing to learn how to do anyway, for a few reasons. One is that it's quite a simple, the methods that they use and the methods that we'll look at today are quite simple techniques for estimating hidden variables in a model, okay? You can apply them not just to aligning words, but to aligning many different things. And the word alignments are useful for building machine translation systems, for building a dictionary, for various things like that. Yeah, sorry.
A good question.
Yeah.
I don't quite get the idea why word alignment itself, so
Yeah.
this idea
Yeah.
by Brown and Guys,
Yep.
is so groundbreaking, so different from phrase-by-phrase methods. I understand that
Yeah.
the data neural stuff
Yeah. Yeah.
is applied to it, but isn't word phrase-by-phrase translation basically the same thing? So you get
Yes, that's totally true. That's totally true. But
so
the phrase-by-phrase translation came after this. The phrase-by-phrase translation is built on top of this, and I can show you that. Okay, so probably, yeah, definitely, the main impact of word alignment is that it allows you to build a phrase-by-phrase system. Okay, so let's look at that. I think it's a very good question. Okay, so let's not look at that. Okay. Do I have a? Maybe I have something here. Let's look. Sorry, I'm just skipping ahead slightly. But what time is 6 o'clock? Okay. No. Okay. No, that's sorry. Sorry, I've got the wrong slides here. Okay, let's just go back there. Let's stick with what we're doing. Okay, so the phrase-by-phrase translation, basically we have, actually no, let me find it here. Oops. Probably I have some slides here. Yeah. Oh yeah, I have them all here. Okay. Let's just look very quickly at this. So I think it's important for you to understand. So I want to spend quite a lot of today looking at word alignment. So what I want to do very briefly is explain how word alignment is used with phrase-based machine translation, okay? Because I think it's kind of the most important motivation for doing word alignment. Okay. Okay. So, data-driven machine translation. Yeah. Data-driven machine translation in general. So any kind of method you want to do is all about in all these. Well, hopefully in these slides I use the same way around. So F is always meant to be a foreign sentence, and E is meant to be the target sentence. So sort of French to English. Okay, and the idea is that if you're building a sort of probabilistic model, you're just going to build something that does this. It takes a French sentence and it tries to find the most probable English sentence. Okay, okay. Now, we said that the training data is sentence by sentence parallel corpora. Yeah, it's English and French, or English and Russian. And we could try to model that directly, yeah? But it might be quite difficult, okay? It might be quite difficult because the size of the input space is huge. There's many different possible French sentences, yeah? Yeah. So doing it just directly might be quite difficult, okay? So, and what these guys in the same paper, when they started suggesting to do word alignment, what they did is they said, let's try to do it this way round. Let's try to choose the English sentence that has it's most probable for being English. So, in other words, let's just say, is the output good output, ignoring the input completely, and let's also model how well it corresponds to the input. Okay, so this is obviously just a simple probability, and the reason they did this is so that you can break down, so that you can train a model that's just good at the English side. Okay, when you train this model here, you don't need parallel corpora. You just need monolingual English text. Yeah, you train what is called usually a language model. Okay, and there is lots more English text than there is parallel text. So parallel text is there's very little parallel text in the world. Okay, it only exists if people translated things. So this we can estimate much better than this. Okay, and we can estimate this thing probably just as well as we can estimate this thing. They're probably because we can estimate them both from parallel text. So we're going to have a benefit if we do it this way by having the ability to use different data. Okay? Okay, so that's what I'm trying to say there. But let me just move on though. But the problem is, okay. The problem is, yes. So here, this is another way to view a word alignment. Okay, so this is another way to use a word alignment. The training data, this is English and Spanish, I think, yeah. So the training data just has these words and these words. It doesn't have this matrix, yeah? This matrix is a word alignment, which we have to learn, okay? But if we can learn this word alignment, then we can use it to break down the probability. So basically, the model, the hard part of the model, which is the probability of a French sentence giving an English sentence, yeah? We can break that down into, let me see, have I got it on here actually? Sorry, this is not quite the slide that I wanted to do. Yeah, we can break it down into phrase by phrase translations, yeah? Okay? If we have a word alignment. And the reason we can do that with a word alignment is that, yeah, here we go. Yeah, so this is a bit, sorry to jump around a bit, but this is basically how phrase-based machine translation works. It takes a sequence of phrases rather than words, okay? And you have some probability. This is just going to be a probabilistic model. So you estimate some probabilistic model over phrases, and this should be an approximation. You factorize your probability of the French given the English into a sequence of phrase-based translations. So you basically assume that each of these translations happens independently, okay? You have a probability for doing that, for doing that, for doing that, for doing that, for doing that. And you have some extra costs to do with how much you move things around. You have an English language model which is scoring how good do these English words go together, yeah? Okay? Okay. But this isn't the main point. The main point is this. If I have the right slides. Yes, here we go. So, the main point is that this is meant to be part of a word alignment matrix. Okay, so it's a word alignment matrix like we saw on the page before. So Okay, so if I say I like potatoes, okay, and we got let's put it like okay, oh no, wait a sec, whoops. J'aime les pommes de terre. So this is hopefully the French for this thing, okay? Okay, so, okay. Okay, so this is meant to be a training sentence. English, I like potatoes. French, j'aime les pommes de terre, okay? Now, if we want to learn a phrase-based model, we need to end up with some probabilities, like what is the probability of pomme de terre given potatoes, okay? Okay? Yeah, so if you want to build a phrase-based model directly, you end up with wanting to build probabilities over phrases. That's at least one way to do it. Now, why might it be difficult to directly build a model over phrases? Why might it be easier to build a model over words, not phrases? So single words rather than phrases. What's more difficult about phrases compared to words?
Different meanings.
Well, actually, probably words have more different meanings on their own. Because, for example, this is actually a good example, because the word pomme in French, on its own, it means apples. But if you say pomme de terre, this means like apples of the earth, then it means potato. So actually, usually a phrase is less ambiguous, yeah, than a single word. Yeah? If I say bank, I could mean riverbank or financial bank, but if I say the World Bank, then you know I mean a World Bank. So the main reason is just the number of parameters. Okay, the number of parameters is just too large. Yeah, phrases, they are many more phrases. Yeah, okay. We want to know the translation of many different French phrases given many different English phrases. It's a really large number of parameters. Okay, and still, we don't have the data. We don't have data all the data we have is this kind of data, which is the whole sentence, yeah? And this sentence, how do we know that we should take this phrase here together with this phrase here? We don't. A priori, we don't know that, okay? All we know is that somewhere in this English sentence is probably, somewhere in this French sentence is somewhere the translation for potatoes. Okay, but at the beginning, we don't know where it is. We have no idea where it is. Maybe it's the word je, which means I, but we don't know that, okay? So the idea with doing word alignment is to try to find out which words on this side and which words on this side seem to have a strong correlation, basically, yeah? And even if we don't use the word alignment directly, or not even if we don't use it directly to do translation, we can use it in many ways. So let me just show you how we use it here. Okay, so and this is exactly how, this is the key point in phrase-based machine translation. So in what you do to do I'm not going to explain at this moment how to do word alignment, but we will do that in a bit. But let's imagine we have a word alignment. So this word is aligned to that. This one's aligned to that. Potatoes, let's say potatoes is aligned to these three ones here, okay? And notice I left this one unaligned. This French word is not aligned to any English word, okay? Okay. So, how do we use this in a phrase-based system? Well, basically in a phrase-based system, we can use this word alignment matrix, as I'm trying to show on this thing here, by we can now take any phrase from the English and any phrase from the French if all the words which are aligned are part of the two phrases. So, for example, I can take out this phrase, I and je, because these two words are only aligned to each other. It's very simple. We can put that into our model. So basically we want to get some allowable phrases, okay? So we want to consider every possible combination of words in the English and words in the French, okay? Every possible one. And the first one we can consider is je and I, okay? Now, are we allowed to take I like and I? No. We can't take that because the word like is aligned to another word here, okay? So this phrase, je, goes to I like. That is not allowed, okay? It's disallowed. The word alignments tell you that that is just not worth considering, okay? On the other hand, we can take this whole phrase and this whole phrase, like je aime, okay? So we can take it like that. And again, we can take, there's many other possibilities, there's lots, there's lots. But actually, with the alignments, you basically can remove bad phrases. Yeah? You use the word alignments to just constrain the phrases. Okay? So the process in a phrase-based system is first, get your parallel sentences. Second, magically do the word alignments. We will learn that. And third, use the word alignments so that you can just take all of the good phrases out. Yeah? And then these phrases, you can estimate a probability. You use them to estimate a probability. But the number of phrases is much less because you use the word alignments. And hopefully, if the word alignments are good, you're choosing good phrases. Okay? Is that clear how we use the word alignments to constrain the set of phrases in the model? Yeah? Does that make sense? Yeah? Okay. So for example, here it's not very clear what to do. So maybe for the phrase potatoes, potatoes is aligned to these three words, yeah? Okay. So I should use different colors. It's not very clear. Using different colors will be better. So potatoes here is aligned to these three words here, yeah? So we can definitely extract pomme de terre going to potatoes. Okay? Question is, what do we do with this poor word here which didn't get aligned to anything? Okay? Well, in practice, people will just include it in the model. Like here, you might include a word which didn't get aligned. It's not an important thing, but okay. But basically, the key part of the phrase-based system is that you build a phrase-level model, and I guess the phrase-based system, the phrase-based approach was suggested first in 2002, 2003, so about 10 years after people first started trying to do word alignments. Okay, so before word alignments, we just had sentences and, well, I guess the amount of memory you need on a computer, even to estimate a word alignments, is quite high, yeah? Because what's the parameters in a model for word alignment? It's probably going to have to give you some idea about the probability of a French word given an English word. So if you have like, I don't know, 100,000 English words and 100,000 French words, then there's potentially a lot of parameters in your model. Yeah? Even if you only give a parameter for the words which occur in the same sentence pair, you still have hundreds of thousands, if not millions, of parameters. Okay? So even word alignment was relatively difficult to do until the 90s. And the phrase-based system, it has billions of parameters in it, but it's a very simple algorithm, and it can be done offline. You can do it basically using techniques such as Hadoop. Okay, so you take your word-aligned data and you produce a model with billions of different phrases. And okay, let's go back. I want to have okay. So the main point here is what word alignment is and why we do it. And how we do it is we do a little bit later today. Okay, so if you have any questions about that, please ask me. Where's the other one?
May I ask
Sure, yeah.
very small question?
Sure, yeah.
Innovation of word alignment was to abandon usage of, so to say, dictionaries.
Yeah, I guess so. So historically, the only kind of this paper, which basically is the first paper to do properly word alignment, is also the first paper which properly tries to learn translation directly from a parallel text. Okay, before that, nobody tried that, and that was another reason, actually. Where did you find a parallel text before 1993? It wasn't so easy, yeah? You couldn't just go on the internet. They used the electronic copy of the Canadian Parliament's proceedings, because Canada, everything has to be translated into English or French, and it's very nicely aligned at the sentence level, and it's people speaking, so the language is a bit simpler, the sentences are a bit shorter, and it's quite a lot of, it's nothing compared to the amount of data that people use now, but one of the main reasons was they got data. I guess, so what they replaced, until this particular approach, people were basically doing rule-based machine translation. And in the rule-based machine translation, they would use a dictionary. And that dictionary would probably be manually created. Yeah, okay. So it's basically they had the idea of learning directly from whole sentences. And the key to doing that was to do word alignment. I mean, maybe it's a very obvious idea, in a sense. It's just that nobody had tried it before. Okay. So let's go quickly. I want to give you guys. We've already been. Okay, I want to give you guys a break, but quickly, let's just. This is roughly what the history of machine translation in 10 minutes. Okay, so this is not. This should be very easy to follow. Probably in 5 minutes. So. So people definitely wanted to do machine translation quite a long time ago. I'm not sure this is the first one, but people had some patents for doing mechanical translation devices, even in the 30s. So this is even before we had proper digital computers. It's not just these guys, but this guy Warren Weaver, who was oh dear, that's badly spelt. But anyway, he was collaborating with Shannon without an extra A, and I guess other people like Turing, and probably lots and lots of scientists and lots of mathematicians in the 1940s were using Bayesian inference. They were starting to use, even people who thought that Bayesian inference was somehow weird, and they realized that actually it's quite useful for doing some kinds of inference problems. So Weaver actually talked about this idea of breaking down the translation, but basically looking at it as a noisy channel problem. Did I put it here? Okay. Then, and this is actually, I should have found that slide. I saw some interesting slides about about the history within the USSR, because there was also a lot of work in Russia as well, which I don't have on these slides. But in the 50s, there was a big experiment. IBM claimed that they were going to, they did this. This is a real translation. I guess they didn't use Cyrillic alphabet, but yeah. The thing is, it's not clear what methods they really were using and how biased their evaluation was. Because what happened was, at first, people became really excited. They had this demonstration of how they can translate from Russian to English, and it really impressed the people who decide in Washington or in Georgetown who to give the funding to for the academic research. And they got the money, and then nothing really happened. It didn't really happen. It didn't really work. So 10 years later, 12 years later, there was basically a really bad time for machine translation. They decided it's not worth it, it doesn't work. And maybe there was many reasons for that, but probably it was because at this point in the 50s, they were doing very, very limited domain, very limited vocabulary. So this system probably only understood a few hundred different words, yeah? So you couldn't give it a new sentence, because most of the words in some new sentence would be unknown to the system, okay? And claiming that the MT would be solved within 3 or 5 years. Okay, I actually heard 2 years ago, there's a researcher at Google who was working on your machine translation, and he also said something very similar to this. I was like, okay. So anyway, in the 60s, they basically stopped doing empirical research, sort of a data-driven research at all. And it wasn't until the 90s. The 90s and now now neural machine translation. Let me show, yeah, here we go. So this is like a graph. This is a graph stolen from Chris Manning's slides. MT quality, and these are the different things happening. And his point is there's lots of remaining problems, and I think I agree. So this is the Georgetown experiment in IBM. This is ALPAC. So you see there was basically no progress. This was another big project, I guess, in the 80s, but still this was mostly symbolic, rule-based machine translation. Then in the 90s you had the statistical machine translation, and then, so this was the word alignment. I'm not sure why it goes down. I don't think it went down. And then this guy, he was basically the founder of Google Translate. In his PhD, he did this, he basically did something using how to use word alignments to get phrases. And it was another really big improvement, actually. In some ways, this idea of using the word alignments to constrain the phrases and building a model which uses phrases directly had more impact on translation quality than the original word alignment. So it's a very simple idea, but it had a much bigger impact when it was put together. And that was in 2003, okay? And then there's one thing mentioned here. This is basically here, where it's quite a slow growth. There's lots of interesting, but relatively, well, there's lots of interesting new models. So people suggest models which are based on tree structures, because language is a tree structure. I mean, usually people think of language as having a tree structure. And to be honest, until this point here, nothing here, I think, has any tree structure at all. Possibly some rule-based system, but nothing that works very well. And here, they tried to build tree-structured phrase-based systems, and it improved a little bit. But basically, I'll be honest, I was in Google Translate from 2007 to 2013, and it improved mainly, this is a bit embarrassing, but it improved mainly because we found more data. Yeah. So, and we spent a lot of, there was some very clever ideas how to find data. When you have huge amounts of data on the internet, how do you find that these two documents are translations and do it efficiently and do it with really large amounts of data? But what we found was that by adding more and more data, we got better. And actually, a lot of the ideas which looked nice and had a good motivation from linguistics maybe, and they worked when you had a small amount of data. They improved from a simpler model to a more complex model. When you have a lot of data, those models don't make a big difference. Okay, so it was a bit disappointing, really. In some ways, it's interesting. Now, that did change. So in 2014-15, as people started to make the newly proposed neural machine translation work on really large amounts of data, then we actually saw the systems getting better, like properly better. And I'm not sure if anybody knows, the Google Translate system changed to using neural machine translation, I think, well, for some languages it was last year. And for Russian and a few other languages, it was just last month. And it's quite noticeably different. I mean, it's still, there's lots of, it's not great, yeah? It's not perfect. Sometimes it looks great, sometimes it still makes stupid mistakes. But basically, that's where we are, okay? So let's stop there, and if you have any questions, let's have a short break. There's some refreshments in the room at the back. And I'm here to answer questions, and yeah.
One question.
Sure. Yeah.
In this alignment, how do we know that G is not aligned, is not good with I like? Like, because there's no one-to-one alignment.
Wait. How do we know that? How we know this is wrong? Yeah, because it violates. Sorry, I didn't explain it, did I? It violates this alignment. If you have the word like is aligned with this.
Yeah.
Now, if you want to take out this phrase, you have to take all the things which are aligned to it.
So if you don't have one-to-one alignment, then it's wrong, basically.
Not one-to-one alignment. It's just that you're not allowed to...
You're not using the fact that like is aligned with...
Yeah.
Okay.
So this is... Yeah, so when you take the words that you choose on this side, you must choose all the words on this side which have an alignment to them.
Is it somehow proof or is it logical?
No. There's nothing theoretical about it.
Okay.
It's just a heuristic. It works quite well. Yeah. There's nothing logical about it. There's nothing here. Yeah.
How do you decide where to put that word?
Yeah, that's a good question. Yeah. So. Depending on the language, sorry, yeah, careful, it's a lot of why is it? Right. So, depending on the language, you might decide to always put it with the phrases afterwards, or always with the phrases before. So in English and French, yeah, it's just heuristic, really. But so in English and French, probably we put it this way because. But if it was Japanese. I don't know if you remember the example I had in Japanese. The preposition goes at the end, and often the preposition is not aligned. If it's not aligned, we put it with the things before it, because we know in Japanese mostly things go to the left. But it's just heuristics.
Thank you.
Yeah, no problem. Yeah. Okay, so now you really are going to need a computer, and what I want you to do is, let me find the examples. Oops. Okay. This is very simple what I want you to do. I want you to start to look at some different machine translations. I want you to go to Bing or Google or Yandex or another, if you want to use a different one, it's fine too, and look at some sentences. Try to translate some sentences from English to Russian, from Russian to English, and make some comments about what's wrong with them or what's good about them, okay? And try to do the same sentence in 2 different systems, okay? So here, this link here is for a, does it work? It should work. I'm not sure how this works though. Let me just put it.
Spreadsheet.
It should be a spreadsheet, yeah. It should be a spreadsheet. It's a bit slow, I'm not sure why. Is it because there's 50 people using the Wi-Fi at the same time? Okay, so actually, this sheet already has lots of examples because I used this sheet earlier with some students in SHAD. But I think it's really good for you to look at the differences. And to try to say which is better, which is worse, and why. Try to understand. Because actually, what you will see is that very quickly you start to understand a bit about why it's making these errors. Even though you don't really know the details of how these different systems work, if you compare them, particularly if you compare the Google and the Yandex ones for Russian, because the Google and the Yandex are now using quite different systems. Okay? Previously, they were both using phrase-based machine translation. Now, because Google is using neural machine translation, you will see it makes very different errors. Okay? So we've only talked a little bit about word alignment and about getting phrases to build a phrase-based system. But I think spend 5 or 10 minutes, do it in pairs, and do at least 3 different sentences, okay? Put them on the spreadsheets, and then I'm going to ask some people to explain what errors they saw and what differences they saw, okay? Is it too slow to access? Yeah? Is it really slow? It's extremely slow, okay. Okay, you don't need to use the spreadsheet. If you can just access. Yep, the link. Yeah, I sent everybody links to the slides in the Google groups. So if you want to have the slides on your computer and look at them, the slides are in the email to the Google group, okay? More people.
Is the link to the spreadsheet?
Yeah, you don't need to use the spreadsheet. If it's too slow, don't use the spreadsheet. But.
Sometimes the link always helps.
Yeah. Oh, I see. Yeah. Yeah. Maybe. Okay. So I want to see if you can find any patterns in the errors. Okay. Okay. Is it too hard to? Okay. 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 I try to approve everybody's membership as fast as possible to that group.
How should I find this group?
It's just this. It's just Google Groups. It's
How do you generate a link to a specific Google group?
I have no idea. I guess I just there's a share. There's an invitation link or something. I don't know. I've never used Google Groups before. Just I didn't know it still existed. I never had my own group.
There should be a direct link to the group.
Direct link to the group. Okay, let me
Because the search function doesn't work for this name.
Oh, really?
Yeah, here it does.
Oh, wow. Okay.
Very nice.
Okay. So this is the club. If you, I mean, it doesn't work for this name. Settings. Maybe I can make it identity, email options. No. Access permissions. It's super slow.
Join requests.
No, join requests is join requests. Okay, but that's I already did that, I think. Anyway, for now, just find some sentences from a newspaper, from Wikipedia, translate them, make sure they're quite short, otherwise it's very difficult. Go to Google, go to Yandex, go to Bing, go to some other translation site and see what the differences are, okay? And do at least a couple of things. Okay. Do you members contact them? So I think is it? Are you waiting for? Because I thought I'd. Okay. I can't see it yet. It's still loading. It's too slow.
Sorry, may I ask you, is it fair to use this assignment to put in some classical? I mean, I put on the Corinne and I feel that probably in some parallel corpora it may exist, right?
Yes, it might. Yeah. Try the first sentence.
Yeah, I mean.
Yeah, that's an interesting way to do it. So.
Does Yandex do it? Because Yandex.
Yeah, but both.
From Russian to English.
Yeah. So.
Yeah. I mean, all happy families resemble one another.
Okay. But how is the translation completed? All happy families resemble each other.
Each unhappy family is unhappy in its own way.
Oh, but that's
So
the real translation. Everyone was a conversion. So you think it's actually Yes, it's.
Yeah, I think they.
So, but they're not. They're probably not cheating. It's not.
It's not cheating. Yeah, I see. It's not. I mean, for our purposes.
No. So it's.
It's not like just generating text.
Yeah, but it's not generated text. They definitely translated that with phrases. So, and probably the length of the phrase that they use, they probably don't use phrases longer than 5 or 6 words. So depending on how long that sentence is, they probably had to still put it together from some pieces. But if you think about it, if it chooses if it has that in the training data, and it chooses the first phrase from that training data exactly the same, then the language model, which is also trained on the same sentence, will prefer to keep using phrases from exactly the same training pair. So it might use only phrases from exactly the same sentence, which is very rare. Usually that's impossible. But so Google has a Latin system, yeah? And for Latin, we really wanted to so translating into Latin, not many people write new things in Latin. So the main use for the Latin system is exactly like this. You should be able to find some parts from existing translations. Yeah? But we have to be careful about copyright. I'm not sure how it works. Yeah.
And only Bing made a mistake.
Okay, so Bing is always has problems.
Like messed up.
All happy families resemble one another. Each unhappy family is unhappy in its own way. That's very good.
Yeah, but
yeah, that's I mean.
The next.
Yeah.
Yeah, and messed up. That's a mistake. But other, I mean.
Everything was in confusion. That's definitely a literary translation.
Yeah.
Yeah? So Michelle is... Everything was confused.
I
And
find the same.
yeah, I guess it's probably a literary translation too, yeah.
Yeah. So.
Yeah. But try changing it slightly. If you change it very, very slightly, see how it deteriorates. Yeah. Okay. So once you've done a few, then we can give some. You can give me some examples, but okay. Mayakovsky is not very easy to translate, I'm sure. Oh, maybe. Okay. Okay, let's get. I'll give you another 5 minutes, and then we'll have some examples and see what sort of things you've seen, because more people requesting to manage members. Oh wow, there's lots of people. Okay. So if you get a chance to put it in the spreadsheet, that makes it easier for us to all see what you did. But какой? To the spreadsheet. Yeah, sure. Sorry. I will send it to the group. Let me send it to the group now. Okay.
It would be hard.
It'd be hard? Or do you want to just get it from here? Oh.
Yeah. We don't have an internet, so it would be easy to just bring from here.
Okay. Just copy it from there. Yeah, sorry if the internet's not very good. Okay? Okay, I'm just going to send it anyway. Let's. How does this thing work? New topic. God, it's so slow. Oops. Okay. Okay. Okay, I should also send that one. Yeah.
Just how will we discuss later maybe how by later are these systems? I mean, if I put will some Google Translator translate the same thing from English that it translated. So the result of English translation into Russian, if we put it back, will it necessarily get more or less the same or the font?
Not necessarily. There used to be a very funny website called Translation Party, where you typed a sentence in English and it would translate it to Japanese and then back to English and then back to Japanese, and it would only show you the English, and it would keep on doing that until it reached equilibrium. And usually at that point the sentence was complete rubbish. So, but there's some features in the model, in the phrase-based model. There's some explicit features which consider the translation in both directions. So it would, in some ways, they would like the model. They would like that to be true, but.
But the model itself is the same. I mean.
No, it's not the same.
When you say that Google Translation is good from English to Russian, does it mean that so the same good algorithm is working on the translation back?
It's a good question. I'll answer it for the whole group in a minute. But yeah, basically it is the same algorithm, but yeah, there's differences. So we can talk about that. Okay. Hey guys. So I don't know. Did you have a chance to look at some sentences? Yeah. Okay. I want to do so many things today, so we don't have much time. So, can somebody give me an example of some problem or something they found in the translations? Yeah? You can explain it in Russian if you want to, it's fine. But what kinds of mistakes did you see? What kinds of mistakes did you see? Yeah?
There is an issue with quoted expressions.
Yes.
Because the translator has to decide whether it is a proper name or it is just a phrase you have to translate.
I see. So you have an example where they translated incorrectly?
Yes.
Is it on the spreadsheet?
It's on the spreadsheet.
Okay, let me do that. Okay. Oh, wow, there's so many things. What, 121? No, 21. This one?
Yes, this one.
Ah, yeah. No. Yeah, no. Okay, so that's Bing. Okay, so I don't know if you can see this. This is number 21 on the... Both sides of the campaign have been accused of using divisive and extreme... Okay, so this is about the referendum. Всех нет избирателей. Нет голосов. So what's... Okay, so let me just see if I remember which one's which. So that's Bing, Google, Yandex. Okay. Let me go back, sorry. So here we go. So Bing, Google, Yandex. So okay. Okay. Wow, the second, this is quite interesting. This one here manages to make this into a separate sentence with Google. Yeah. So so this is a difficult thing. The problem with the phrase-based machine translation is it treats everything very literally. So I'm not sure exactly why they keep the same word there, but it may have been that there's some examples where it wasn't translated. But this is phrase-based machine translation because this one is Bing, this one is Yandex, this is also phrase-based. So let's just look at those a bit more detail. No, it's relatively BT. Yeah, so what's going on there? So you have, so what I think you can notice here as well as that is this correct? It seems like the ending is wrong there, yeah? It's not correct at all, yeah?
Totally wrong.
Yeah, okay, that's a good way to put it. How about this one? It's better, yeah? Yeah. So we don't know why yet because we haven't really, well, I'm not sure you will learn why, but it's a fact that the neural machine translation, one of the defining features is it makes the language more coherent. It joins things together better, which means that in Russian, it usually has better endings, better morphology.
Yeah, but it fails when the sentence is long.
Oh yes, when the sentence is long, it can become completely stupid. It can be completely wrong in a way which the phrase base will probably not do. But so what you know, I was describing on here how you do some word alignment and then you take some of the phrases and you build a model with phrases. Now, when you do that in French, yeah, we took the phrase les pommes de terre and the word potatoes, yeah? Imagine this was Russian, yeah? If this was kartoshki or skartoshkami, it would come out still with potatoes. So there's no way that the model doesn't really know, yeah? It will probably, if it has the word s in Russian, it will often have the right case, the instrumental, but it doesn't do anything to try to make that happen explicitly. And you take these phrases from one part of the sentence and you can use them in lots of different places. And very often in Russian, that means you're using a phrase from one context in a completely different context where the ending should change. So I think probably it's a little bit obvious that the basic algorithm for phrase-based is breaking lots of the rules of Russian grammar. Yeah? It takes everything out of context. In English, it's not such a big problem because in English, you have the word potatoes, it's potatoes. It doesn't matter if it's with potatoes or the potatoes fell off the lorry or the potatoes killed somebody, it's still potatoes. But in Russian, these would all have different endings. And so that's one of the reasons that the phrase-based system is not so good there, yeah? Same with, I guess same with here. Yeah, and this is quite nice. This is, yeah. Okay, how about some other examples? Did you have an example?
Yeah, with the Apple one.
The Apple one, okay. What's going on here then? So which one's doing better there?
I'm not sure. I think Google and Yandex are pretty on the same
They're pretty
level.
good. Yeah, okay. It'd be nice to see an example of the Google neural machine translation doing really badly. Because it's possible to find, it really is. I mean, on average, it's a bit better, but it's interesting to find where it fails. So this is Apple разработала. Yeah. This is, yeah.
Basically, everyone fails at the ending part.
Okay, yeah. Discovered by Business Insider via Republic. What? Business Insider? Ah, wait a second, but where did Business Insider go here? I don't even see it. What's the translation for Business Insider? Business Insider is the name of a a magazine, I think, yeah? So, do you think?
Yeah, I think.
So if you go to Yandex, you can actually put probably you can see which phrase went from where. So translated it through Yandex.
I changed, I think I have.
Oh, okay, fair enough, okay. Oh, but now it's the same as, isn't it the same as Google now? Okay.
Identical to Google.
Oh, actually, yeah.
Yeah, wait a second.
Yeah,
I think you've just.
The Yandex is the second column, correct?
Let's go here. Yandex should be the third column because it's in alphabetical order. And let me just do it. Let me translate it on Yandex now.
Omitted the business insider part.
Yeah. So that is a remarkably common thing in translation, and it's weird. Yeah. So let's have a look. This is actually Yandex Translate, and where are we? Business Insider. Is there anywhere that? No, it's not being completely. This is something that you can see on Yandex. Unfortunately, with the new neural system in Google, they don't show you this. But what it's showing here, I don't know because I don't know exactly what Yandex did, but I guess it's the same as what Google used to do, and they show to the user which phrase was used. So this, when I put my mouse here, calendaria, means it came from this phrase. So phrase-based machine translation, one very fundamental feature is that every phrase in the input is used exactly once. Okay, so you translate the one phrase once. And once you've translated it, you can't use that phrase again. So this phrase here has to be translated. It could be translated to an empty string, but they translate it to the calendaria.
But
so
why they didn't get that it's like the name, because it's in capital letters, starts with capital letters.
Names are really difficult. And unless you have a system which recognizes this is a name, so maybe names get translated differently. Yeah. Name of a person, maybe you don't even need to translate it, yeah? You just copy the string. So same for dates, same for numbers, same for street addresses. All these things are quite hard to translate without recognizing the semantics. So if you don't understand that this is
just by the capitalization of the word.
Yeah, you're right. It is a bit surprising they didn't get it right. But what did Bing do? Should we just... But it's very common to get this kind of thing. It's Bing Translate? I'm not sure what the... Okay. So the...
Bing.com/translator.
Oh, sorry, yeah. Okay, here we go, yeah. It's a bit small. Oh. Translate to what?
On the right side, I think.
Is it? It's not doing much. Okay. Oh well.
I have inputted the Bing version into the Google Translate.
Oh, you put it on here. Okay.
This time.
So this one, yeah? Bing is the first. Bing is the first column, okay. But it's already Okay. Business Insiders. Yeah. So they also translate it as a. They get it a bit wrong, yeah.
Yeah, but it's better than.
It's better. It's better than the Yandex one. Yeah. Are there any other examples that people have that show something different from what we've seen? Is there something? If there's anything interesting that somebody found that you want to, because I have some other examples. I want to show one or two, but. Okay. Let me show my example. This is one of the examples that came up earlier. This came up in another class. This is just a random example. So
what number is it?
It's number 4. Number 4. So yeah, it's very hard to read. Number 4, and no, okay. So where is it? Actually, wait a sec. Maybe this isn't the one.
Is there such a word?
What's that? The axle. Well, it's a typo, isn't it? yeah. Actually, maybe it was in the other direction. It was in the other direction. Actually, what you can see here, this is the wrong example, sorry, but what you have here is you have a misspelling, which gets, I guess... Trebuchet is an English word. It's a very rare word.
No, I mean,
but
Bing does not.
Yeah. Okay, but what does Google do?
They should is.
Yeah, now this is interesting. We will see, but let me show you the other way around. There's something strange happening in Google. I'm not sure, I didn't actually, I'm just guessing, but let's find the one with the trebuchet in here. Where was it? I thought it was in here. Okay, yeah. So look at this one. This is also sentence 4, but it's on the other sheets. It's on the Russian to English. Sentence 4 on the Russian to English. Now, you have a Russian sentence where they talk about trebuchet. Yeah. Now, it's a very rare word. Yeah, very rare. I don't really know what it means. Maybe it's more common in Russian, but it's definitely not common in English. It's like catapult, yeah? Okay. So it's kind of catapult, yeah? Okay, that's what, yeah, now, what does the Google, how does the Google one translate the word trebuchet?
So it was a mistake and corrected to trebuchet.
Yeah, well, yes, exactly. So it's in this direction it translated trebuchet to something based on trebuce, and in the other direction it translated trebuchet to treshutz.
Yeah, like sound of it.
Yeah. Now, I don't know why that happened. I don't know exactly what Google is doing, but I do know that in order to make neural machine translation work, you need to reduce the size of the vocabulary. So phrase-based machine translation generally has a completely open vocabulary. That means every word you see in the training data you can use in the translation. Yeah? You don't throw any words away. For computational reasons, the neural machine translation would be much too slow if it had the full vocabulary. So the full vocabulary for a phrase-based system is easily 1 million words. Okay, easily. It can be much more, but it can easily be 1 million words. Neural machine translation usually only has a vocabulary of less than 100,000. Okay, maybe a lot less than 100,000. Okay, and I will explain tomorrow why why they do that. But if we know that, then we can probably see that what's happening here is because they are breaking the words into smaller parts, which have to make the vocabulary smaller. Okay, probably that's what's happening. Okay, so you get some very strange errors, but in general, the translations are better with the neural machine translation. Okay. So if there's any more questions, any questions about what we've been looking at here, so you sort of. Do you understand a little bit, at least, about if you know the way we get the phrases for the phrase-based, maybe now you can understand when you stick them all together to make a translation why you get such strange morphology, yeah? Okay. Let's move on then. Okay, so what I want to do is, this is actually the, we don't have much time, do we? But I have sent you all some slides, okay? So I've sent you all the slides. These slides are in some ways way too easy probably for you guys. But, where are we? Statistical modeling. What I want to do is I actually want to, okay, so probably I won't really use these slides. I just go very quickly. But I want to get you guys to build word alignment models. Okay, very simple word alignment. So I want that means I'm going to give you some data, some parallel sentences, like this, with no matrix. And we're going to build an algorithm that can learn the word alignments, okay? And we can learn the word alignments on your laptop using Python, if you have Python. And we will use an algorithm which is called the Expectation-Maximization algorithm, okay? So this is a very general algorithm for learning hidden variables, okay, learning with hidden variables. And it's actually rather simple when you use it, but usually when people describe it, it can often sound quite complicated, and the explanation about why this algorithm works can be a little bit hard to understand. But I think that doing word alignments with this, you'll be able to understand it very well, okay? So what I want to do now is understand what your background is in statistics, basically. Okay, so simple statistics. If I have a coin, and I don't know if this coin is biased, yeah? I don't know if it's always 50%, or half the time heads, half the time tails. How can I find out what the probability of heads is with the coin? What should I do? Yeah, flip the coin and do what? Just flip it multiple times and record the results. Yeah, okay. Flip it multiple times, how many times?
Many enough.
Many enough, okay. And then, so I flip it, and then I record how often it becomes heads. Okay, and then?
Then you divide it by the overall.
Exactly, yeah. Obviously, yeah. Okay, so everybody's probably familiar with the very basic statistics, yeah. So that's actually its maximum likelihood estimation for the parameter for that model. How about so I'm sure you know how to estimate parameters, simple parameters for models, but how about conditional probability? Bayesian. Who said that? I can't hear. Yeah. Okay. Okay.
I mean, the majority already knows.
Yeah. Sure. I hope. Okay. So I think let's go straight through then. Let's go through all of this. This is all. Okay. So who can answer this question? Actually, I don't know what the answer is, but sorry. This is Bayesian. This is, well, if you use Bayes, it'll be easier. Okay, so there's a school with 60% boys and 40% girls. Okay, so almost half and half. And the female students wear trousers or skirts in equal numbers. So 50% of the girls and 50% of the girls wear trousers and 50% of them wear skirts. The boys all wear trousers. Okay. Passerby sees a random student from a distance wearing trousers. What is the probability that the student is a girl? I don't really want to know the number. I just want to know, how do you compute that number?
Straightforward application of the Bayes formula.
The straightforward application of the Bayes formula. Okay. Cool. Yeah? Yeah? Okay, cool. Okay. So let's actually try. So straightforward application of the Bayes formula. Well, actually, okay. I won't make anybody do it, but I think if you in a moment we will start to do some practical things. So if you're not sure about this question, please try to do it on a piece of paper. Okay. Now, so this is the practical exercise, and this is actually, no, this isn't quite yet. This is the precursor to the practical exercise. So, you have a bag of coins. Okay, there's a bag of coins. This bag of coins has red and blue coins inside. Okay, and your friend has a bag. He draws coins at random and tosses each coin n times. Okay, and he records what he sees. So he records that he saw a blue coin and he got 3 heads. Okay, he saw a red coin and he got 2 tails and 1 head. Okay, each time he puts the coin back in the bag. Okay, so it stays simple. Okay. So here you have some data. Yeah, you have 2 different coins, red and blue, and you have heads and tails. Okay. So if we're looking at this data, one question we can ask is, what model could we use to just describe this data? Yeah? What's the simplest parameters you could use? So, sorry, I don't know your name, but you mentioned before you estimated the single parameter for 1 coin, yeah? Okay. So the model that you estimated has 1 parameter. My first question here is, what parameters could you use to model this data? It's not a trick question. Just how many parameters would you use? If we don't know, sorry, I missed one very important thing. The coins with the same color all have the same probability of heads and tails. So, yeah.
Is there 3 parameters?
So there's 3 parameters. Yes, I think that's one way to do it. So what would the 3 parameters be?
The percentage of the red coins.
Yes. So let's write them down. So we got the that's not a good color. So we got 3. I think we've got 3 parameters. Yeah. Yep. The probability. Let's call it red. Okay. Probability of red. Okay. That's our estimate of the probability. So I use these things for parameters. Okay. What's the other what are the other parameters?
Prices for the red and blue coins respectively.
Yeah. Okay. So let's say head for reds, which is the probability of heads given a red coin. Okay, so that once we chose a red coin, what's the probability we're going to see heads? And also, what's the probability of heads for a blue coin? Okay. Okay. So it's 3 parameters. Yeah, 3 parameters. So next obvious question, because it's on the slide. How do you estimate these 3 parameters? Again, this is very simple, I know, but it will get more difficult, don't we? How would you estimate these parameters? Anybody?
The first one is completely straightforward.
So the first one you already estimate. Well, so yeah, the first one you would estimate by taking what
the fraction of the red coins that you.
The fraction of the red coins that you draw. Yeah. Okay. How about this one? Maybe somebody towards the back so that they don't fall asleep. How would you estimate the probability of heads given red? What do you do? What do you need to count?
You toss every time for red.
Yeah?
You do the same counting.
I know it's so obvious, but still. Yeah. So what's the statistic you need? That's the question. What's the statistic? There's something you need to count. You need to count the number of times you saw heads while you were flipping a red coin. Yeah, exactly. So there's 3 parameters and there's 3 different statistics. So these are the 3 parameters. The 3 statistics are the number of times you draw a red coin. If you count that, then you can estimate the parameter. There's the number of times you saw heads when it was a red coin, and the number of times you saw heads when it was a blue coin. If you count those 3 things, then you can estimate these parameters, yeah? Okay? And this, yeah.
I'm sorry, I don't get what does mean second and third?
The 2 parameters, it's the probability of heads if you chose a red coin. So let me draw this out. Yeah. Sorry, I should have made a nice drawing in the slide, but it's not very clear. Okay. Oops. Okay. So we have this big bag with lots of coins in it. we get a red coin, and then and then we flip it and we get heads, heads, tails, heads, let's say. And we have a blue. We pick out another coin, and this time it's blue, and we pick out another coin, again it's blue, and each of these we get just, let's say, tails, 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 heads. Tails, 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 tails. Okay? So, oops. So I just did 3 samples. I chose 3 different coins, and I flipped each one 4 times. So, this is a very small sample. This is not going to be a good estimate. But if I did it hundreds of times, I would be able to see the fraction of red to blue, and that would be this thing. And then to estimate the probability of heads for red, I would take all of the red examples, and hopefully there'll be some more, and I would count how many times heads happen. Yeah. So it's I think you. Yeah. Yeah. Okay. Let's see. I think probably my feeling is that probably in this room there's a lot of people who are like, this is ridiculously simple. What's he talking about? And there's maybe some people who don't find it so simple. So actually, we can probably do 2 different problems now that are quite different, okay, but based on the same data. So this is the first problem, and I will give you a script that simulates this thing, and what you can do if you want to is you can implement the parameter estimation, okay? If that seems way too easy, and I hope it does to some people, but it doesn't matter, it's fine if it doesn't seem too easy, then there's another one. And this isn't quite so easy, okay? It's exactly the same data, but your friend took this bag and he dropped it in the bath. And now the paint came off all the coins, okay? So now you don't see the coin's color when you take it out of the bag. They all look exactly the same. Now we know that there's 2 kinds of coins, so we can still try to estimate exactly the same model. The question is how you do it, okay? So this problem is basically exactly the problem that you need to solve for word alignment. I'll explain how the 2 relate in a minute, but this is the problem of trying to estimate parameters from hidden data, okay? So in the word alignment problem, you have a sequence of words and a sequence of words, and you don't know which ones correspond to each other. Here, you don't know what color the coin is, okay? Okay. So the solution to both problems, there is one solution that is actually remarkably similar between the 2 things, okay? So can I just ask people, who wants to do the first problem and who wants to do the second problem? Who wants to do the first problem? Nobody. Yeah? First problem. Okay, cool. I would say that. Okay, so I'm going to send you, so I don't know how this will work now, but I'm going to send 2 Python scripts on an email. One will be called coins, and one will be called hidden coins. And you can choose which one you want. In fact, yeah, you can, let me just send that now. Okay. So you'll need Python. Yep. Oh, you can't access the. Oh, for this, yes, sure. Yeah. Yes, if you're not a member of this, then you. Where is it? Right. So. By the way, for the second problem where you don't have the color, you're not guaranteed. You can't really guarantee much. You can't guarantee that you will. Where the hell? Sorry, I'm trying to find this.
У нас есть сэмплы из неизвестных каких-то студий. Нам известно, что у нас есть одно. Ну, точнее не так. У нас есть сумма.
Where the hell?
Нам нужно оценить их от ожидания.
Sorry, I don't know how to use this thing.
It said that my membership is pending.
Yeah, okay, so where do I see the methods? Can I just send this, can I just quickly send these emails? So this to Python. These are Python 2.7 because I still use old school Python.
Just like Google.
Yeah, exactly. Is there anything else? They have 3? Oh. So there's two scripts here. Probably, even if you're more interested in the hard task, you can just solve the simple one, and then the way I wrote the code, you can use the methods from the simple task in the more difficult task. So probably everybody should try to look at the simpler one first, the coins example. But let me just send this. It looks like you may be trying to post. Oh, cancel. Oh, that's all right. Scripts. Okay. So I just sent that, and now I'll approve your membership. Recently viewed. Oh, manage. Sorry, I've got it now. So if you can download those scripts, I sent 2 scripts. If you can download them, so I'm going to try to approve people's membership, but they're very small scripts, so it should be easy to download. Okay, I have absolutely no internet connection. I'm sorry, I can't get on the site at the moment. I'll approve it in a minute. But, okay. That's where they go. Oops. Yeah, I guess everybody's trying to use the internet, so nobody can.
It's pretty dense.
It's pretty what?
Dense.
Okay, so you don't have to read the script. Just run it, and something will fail, and just go to that method. Yeah, it is a bit. Most of the script is not doing interesting things. It's just generating data and printing things, but. The interesting part is just like 1 or 2. So okay, there's lots of people. There we go, approve. Yeah? Does anybody else want to get approval for this group? It seems like there's more people here than in the group, I'm not sure. Okay. So.
Нет, мне не пришло письмо почему-то.
Я прям выпил.
А, выбежал уже.
Да.
Все понял.
Надо здесь листать. То есть почти уже. Почти. Почти совсем.
So, so if you run this, I'm not sure if you can see this. Can you see this at all? Okay. So if you run if you just write Python coins, so this is the first one. If you run it and you enter probability, like let's say we choose the reds with probability 0.2, and we have mostly heads for the red coin and mostly tails for the blue coin, and let's flip 100 coins each 5 times, okay? Okay, what it does is it generates all the data, and it fails in one specific method, which is where you're meant to estimate the parameters. And implementing that method is probably the first thing to do, okay? This is obviously very simple to do if you understand maximum likelihood estimation. But once you've done that, then you can use your solution in the second script, okay? So let me just so it should say where it is. Okay, so just in this area, that's completely impossible to read, sorry. Let me change my terminal. Preferences, profile, edit. So I would start by implementing the simple one. Is this going to change the colors? Yes, so I actually, it's impossible to read, sorry. And I don't know how to change my. So there's.
Do you have Sublime?
No. So anyway, there's 2 methods which you need to implement. One just gets the counts, the statistics, and one gets the probabilities, okay? For some reason I get, whatever, okay? So you just have to count the things and then you have to estimate something. But okay, so I will just cheat because I don't want to have to. What's that? Really? Is there something else what do you use? V?
Sublime and V.
Every time I get in V, I have to close the terminal. I don't understand how to use it. So let me just show you what the solution should do. Basically, once you have the solution, then you can put in the probabilities like this, flip 100 coins 10 times each, and what it does is it generates, what it will do, if you just, it's very simple, and I'll send you the solution, but it will generate the data, that's already there. What it does is it counts how many times each of these things happened, and then it estimates the probabilities. And the main thing that I want you to see here is just that, you know, your estimates can be quite reasonable, yeah? Okay? So I only used 100 coins and I tossed each one 10 times, and we get estimates which are pretty close to the true parameters, okay? 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 So, okay. So for people who, do people have questions about how to implement this? Because I'm quite happy just to give you the script because I don't want to run out of time. And I want to get back to machine translation, otherwise I forgot. We're meant to be talking about machine translation. So, do you understand the 2 things you need to implement in this script? Yeah? You need to get statistics and you need to get things. Okay, in that case, let's just pretend you did it and I will send you the I will send you the solution. Coins solution. And you will then all try to access it. And okay. Because okay, so that's I've just sent that. No, come on. Sorry, God, it's so slow. Oh God. Yeah, I'm gonna. I can't tether. Probably it doesn't work.
You can connect to mine. It's faster.
Yeah, could I? What is it?
Android AP.
Okay. And what's the password though? Actually, I've got an Android AP already on here. Okay, thanks. A second, sorry. That's really good of you.
You probably shouldn't display the password.
Yeah.
That access point here.
No, that's all right. Actually, I shouldn't put it on here, should I? So I can't put it on here without. Yeah, it's all right. I'll use this. I've got back on. Yeah. Here we go. I'll do it. Post. Is that attached? Oh God. Okay. So this is the. No. Yes, just do it. But I want to. Yeah. Okay. So here's. Yeah. It looks like yes, it's fine. Okay. So that's the solution which gives you these kinds of results. Okay. I've sent you the script which will do this for you. Yeah. And the main point is that this is a very basic idea that you're using, which is called maximum likelihood. You're taking some data, you're choosing the parameters which maximize the likelihood, okay? And you can show that by writing down the likelihood of the data. So, where's my pen?
I think the document is broke.
Yeah.
Oh, really? Didn't get attached?
It's too far.
Okay. Sorry about this. Well, the solution, yeah? It didn't. Okay. But I thought you'd already implemented it. I just sent it in case there's some people who hadn't managed. But okay. Coins solution. Post. Okay. Okay. Oh. Okay. So, okay. Yeah, so let's. I think it's best if I go back to the thing. Okay, I'm clearly not going to get to finish all this today, so. But so there's no point to rush.
We still have an hour.
Yeah, I know, but there's lots. Okay. What I want to do is make sure it's so obvious when you're given the problem when you're given the problem like this and you have the colors and you have the data, it's so obvious what is the right answer that you can do it almost without thinking, yeah? Which is a little bit of a problem, because when you make the problem more difficult, when you get rid of the color, then you need to start to think a little bit more carefully about what you were doing originally, okay? So what you were doing originally, let's be a little bit more precise. Let's be a little bit more abstract. So you have some data, okay? The data in this case consists of, we'll say, two different random variables, x and z, okay? Let's think of it like this. Let's think of x as being the heads and tails. So x is the heads and tails, and z is the color, So Z, they're both binary variables. Z can be red or blue. X can be heads or tails. Okay? And what you were doing when you were just counting the things here and dividing and getting the parameters is you were actually estimating them by maximizing this function. Okay? You might not have thought you were doing that, but you were. Okay? And you could show that by taking the derivatives and working out where the maximum of this function is. But this function makes a couple of assumptions. They're very common assumptions, but it's worth thinking about them. So, firstly, x and z, it's a product. I'm breaking this thing down into a product. What does that mean mathematically? Well, not mathematically, statistically, what does that mean?
There's independent.
Yeah. I'm assuming that every time I take a coin out of here, the probability of what happens is completely independent of the things that happen before. That is a very reasonable assumption for this problem. Okay? It's an assumption that we will also make for the machine translation models, but maybe it's not very reasonable assumption there, but we need to do it. It makes things much simpler. Yeah? By making this into a product and then taking a logarithm and converting it into a sum, it's much easier to maximize the function. Okay? Okay? So from now on, we will think of x as the things that you see, and z are maybe the things that you don't see. Okay? So this is, let's okay. Okay, sorry, so I already have that here. Yeah, okay. So what I was trying to say is that in order to find the parameters which maximize the data, okay, so actually I didn't explain one thing. Why do you want to maximize the likelihood of the data? Why is that a good idea? Why does that make sense?
In which universe the things that we see are most likely?
Yeah, you're sort of trying to say, I'm going to try to make what I actually saw the most likely thing to see. Yeah, fair enough, yeah. Yeah, it's a principle that people use. I don't think there's probably lots of debates about it, but I'm just, yeah. Okay, so we want to choose the parameters to maximize this thing, which is the same as this product, which is the same as this sum. And what I did here, this line here, is a little bit weird, because up to here, x and z are just elements in our data set. We have a data set, we have the coin, which is the color is, we have the flips, which is the x, and we have the color, which is the z, and like that. Now, what I'm saying is you can change this and just do it by taking the statistics. So this is meant to be the count. I use this to mean the count. So how many times did I see heads with blue? How many times did I see heads with red? Okay? And I can use those statistics, and it's exactly the same mathematically, okay? Okay? Now, this is all very well, but let's not do that. Okay. Now, if we don't have, actually, sorry, before you see that, so if you don't have the counts, if you don't have the observations of the coin, yeah, if you don't know what the coin's color is, how would you possibly do anything here? If you don't know what z is, you know x, you've seen some heads and tails, but you don't know the color. What could you possibly do? Okay, because this formula relies completely on counting how many times did we see heads and blue, how many times did we see heads and red, tails and blue, tails and red. If we don't see the color, what could we possibly do? What could we? Yeah, so at the back. Yeah.
We pretend that we see them.
Yeah, we could pretend. And how would you pretend that you saw them?
Randomly choose.
Randomly choose. Wow. No, that's not a bad way to start. In fact, that's not a bad way at all to start. Yeah? Yeah, go on.
So, I had an idea to clusterize the results.
Cluster the. Okay, that's a very good idea. So, and especially with this problem because where's the thing? So, yeah. So I hope you can see at the back. Sorry. So now we don't know the colors. Yeah, we just have black. We have black coins for all of them. So you would sort them, maybe sort them by the number of heads. Yeah. So you could group together. Maybe you decide to group this together, and you decide to group this one together because this one has a lot of heads in it, and these ones have lots of tails in them. Okay. So if you cluster them, if you cluster them, and in this particular case, it's so simple because you just have heads and tails. So you could sort all of your examples by the number of heads. Yeah. So then the ones with the most heads at the top and the fewest heads at the bottom. And then you choose some place in the middle. And what do you do then? What were you going to do afterwards? How were you going to choose the place in the middle? The dividing line.
There are lots of ways to do this.
There's lots. Yeah. Okay. Fair enough. Yeah.
So the simplest one to just choose the most difference.
Yeah. The place where it differs the most. Okay. Yeah, that's one way to do it. Yeah. So you could choose a place to do it. And okay, once you've done that, what can you do next? Oh, you just say this is all blue and these are all red. End of it. Oh, I see. Okay, but then your CPU wouldn't be working for very long, and that's not what we're paid for. So we should think of a solution that requires more CPU cycles. But it's a very good idea. That's exactly, I think, maybe when you're saying randomly, that's a good way to start as well. But
We have to throw each coin more times so that they will flip more obviously.
yeah, that's completely true. So it's remember with the original problem where you can see the colors, it doesn't really make any difference if you you take the coin, flip it once, take another coin, flip it once. It doesn't really matter. Yeah? If you do that, actually, you get a better idea how many red coins, how many blue coins. If you just flip each coin once now, then it's really hard to do anything. Yeah? You just take all the heads as one and all the tails as another. Yeah. So, very good point. You should try to sample each one more times. Yeah. Okay.
You mean the existing ones that we have already sampled?
Yes. So what I mean is, I'm going to get pens. So so can you just elaborate? Can you say why you're suggesting that each time we choose a coin, we should flip it more times if we can? If you can flip each one 10,000 times, then you can really see. Yes, you should. That's a very good point. Yes. Yes. True. So it's a very interesting point. If you are allowed to flip each coin a very long time, then we can solve the problem. Because if you can they should all, by the law of large numbers, they should all tend to the mean there. But what about if we're not? So in machine translation, we don't have infinite amounts of data. We can't sample translations millions of times. Okay, what can we?
Well, what we're looking at is a sum of two binomial distributions.
It's a sum of two binomial distributions. Okay, yes, that's true.
Trying to do is to estimate their means.
We're trying to estimate their means and the distribution that chooses between them. Yeah, it's a bimodal. It's a mixture of Bernoullis, I guess, is the right way to put it. Yeah.
Well, maybe there is a statistical test that does exactly that, but off the top of my head, I haven't.
Yeah, no, maybe there is. That's a good point. But that's not what I'm looking for at the moment. What I'm just thinking is, once you've clustered, so let's assume that you were allowed to flip them, say, 10 times, yeah. And let's assume that the probabilities for the reds and the blue coins are reasonably different, yeah? what can we try to do? Could anybody think of an iterative process that would allow us to do something? So you suggested clustering. You get the ones with all the heads, ones with all the tails, cluster, and then what could you do again? Yeah, so I mean, actually, what you can do, and there's an algorithm. So there's an algorithm. There's a whole family of algorithms. From one extreme is called k-means, which you've probably heard of k-means. Yeah, I'm sure you've heard of k-means, but maybe you wouldn't think of it in this context. But you can use k-means in this context. So k-means, we know in this case that k is 2. Yeah, there's two different distributions. K-means you just choose 2 random values for your parameters. So you set these parameters at the beginning. You set them completely randomly. Okay. The only important thing is they must be different. Okay. So you say we'll choose this, and then you look at each sample, and you try to compute. You try to use Bayes' rule. And you use Bayes' rule. Bayes' rule is the key thing here. You use Bayes' rule to compute the probability of, so you know, you have these parameters, yeah? So you got the probability of red. You know that parameter. You know the probability of heads given red, yeah? Because you've fixed these parameters, you chose them randomly, yeah? What you want to compute now is the probability of red given some data. So let's say we see TTT, yeah? Okay? So if you can use Bayes' rule, yeah? You can use Bayes' rule, yeah? With these parameters, you can compute this, yeah? If you know these 2 numbers, yeah? Can you? What's it going to be? What's the probability? If I know the probability of red is this thing here, and the probability of heads given red is this thing here, what's the probability? Well, let's make it simpler. Let's make it heads. Otherwise, I have to write more. Head, 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 head. What's the probability of that? It's just a simple application of Bayes' rule. I didn't say that. Oh, come on. So you just have to put down, it's going to be if you write it down first, you just have to put, it's the probability of red and the probability of all of these heads given red, yeah? Divided by something else, okay? And this thing, they're all independent, okay? So it's I think I have it on the slides, actually. Do I have it on the slides? Okay, I'm afraid I don't have it on the slides, but okay, what your task is now is to I don't want to lose you in this. Let me just go back to this. Okay. So what you could do is if you could compute the probability of red given the data, then in k-means, all you have to do is you say, well, is the probability of red higher than the probability of blue? And if it's higher, then you assign that data to blue, okay? If it's lower, if the probability of red is higher, you say it's red. And essentially, you just label the data using the posterior probability, okay? And then you re-estimate your parameters using the labeling. So you basically, you choose some parameters, you infer the posterior distribution given the parameters and the data, then you re-estimate the parameters, then you re-estimate the posterior, then you re-estimate the parameters backwards and forwards, and each time you do that, it will increase the likelihood of the data, okay? I really am not going to have time to go into the details of this, but...
Does it guarantee convergence to the global
No, no, it doesn't. It doesn't guarantee convergence to. It's guaranteed to converge, but it's not guaranteed to converge to a global maximum. It will in certain situations. It will, yeah. Actually, I think you can show quite easily that if this is uniform, if this is 0.5, then it will converge to the global maximum. But if this is unknown, then it won't. Or it's not guaranteed to anyway. But the point is, you basically deal with this thing. You basically have gone from this is the normal maximum likelihood estimate, yeah, where you just said we're going to take each example in our. This is one way to write this. What I'm writing here is these are the parameters. We want to choose the parameters to maximize this. This is every example like this from our data, the probability of it. Okay, now, a different way to write this is just to put this weird little function in and to sum over all the different possible values. Okay? Now, that's a very strange way to write down maximum likelihood estimation. And if you write it that way, it doesn't help you to do maximum likelihood, but it does help you to see the connection to this algorithm. This algorithm uses, instead of this ones or zeros, it uses the probability of red or blue given the data and given the current parameters. So this is basically saying we're going to wait. So if we have an example like this, okay, this example here is all tails. So maybe the posterior probability of red is very high. So we're going to say that this is like 90% red, okay? And when we collect our statistics, we're going to collect 90% red from here. This one here is not so clearly red. It's sort of more red than blue, but it's more like 60% red. So we're going to weight this with 60% red and 40% blue. This is going to be 90% red and 10% blue. And this one maybe is going to be 90% blue and 10% red. So we use the posterior distribution as like a fractional count. So it's exactly the same as normal maximum likelihood, but in normal maximum likelihood, you have 1 or 0. It's either red or blue. It's red with probability 1, it's blue with probability 0. In this setting, we have a probability, and we just count. We just count exactly the same things. The only difference is that in this algorithm, we have to first look at the data, use our parameters to estimate the posterior distribution over the hidden data. Okay? Okay? So you estimate the hidden distribution, the posterior distribution over the hidden data. And then use that to re-estimate the parameters. Okay? I feel like I might have spoken too much. Okay. So maybe looking at the slides will help you understand this. Sure, sure.
So we are using the previous experiment to calculate the next one.
The data is fixed. Okay, the data is all fixed. We have sampled maybe 100 different coins, and we flipped each coin 10 times. So the data is fixed. Yeah, we can't make more data in real life. The data is fixed. We choose some. We have unknown parameters, theta. We have unknown labels, blue or red, which we call Z. Both of these things are unknown, which is kind of troubling. Yeah? If we knew the parameters, probably we could guess the most likely label. If we knew the label, we could easily compute the parameters. But we don't know either. Yeah? We want to know the parameters, theta, and we sort of need to know the labels too. So the labels are kind of something that helps us. Okay? Now, so what we do is we guess one, we pretend it's right, we infer the other one using Bayes' rule, we then re-estimate the other backwards and forwards, and I really don't. It's too late on Saturday evening to look at the proof for convergence and all that. But there's 2 pages showing you how it works. It's actually not very difficult, and it works very nicely. It will. So in this particular problem, it will work quite well. Okay? Apart from there's one problem. There's one problem. One thing it can never do right.
Choose the first one.
Well, let me tell you that if you give it enough data, it will estimate these parameters correctly, apart from it might have the red and the blue switched round. Yeah? It never sees any real labels, so it can never correctly guess which is red and which is blue. But what's the time now? It's 20 past. Okay. I think you should try to. So I sent you the solution, and I think what we should do is just to finish, because if we finish with a practical session, then it gives you time to ask me questions. Okay? So I sent already. What did I send you already? I sent you some. Let me. Don't all use the internet now. I sent you. Did I send you this one? The solution? Did I send you? I'll send it again anyway. Oh no, you're using it.
Switching to the hidden problem or to the
No, the hidden problem I didn't send a solution to. I want you guys to do that. Did I send this one already? Coins Emily solution. Okay. Yes, it's fine. Don't worry.
Yeah, I've sent it.
I've already sent it. Okay, sorry, I sent it twice. Okay. So let's go to the actual thing. So you should have Coins example solution. Let's put that in there. Oops. Okay. And I want you to solve the hidden one. Oh no, actually wait a sec, this isn't going to work. Yeah. Okay. So all that was in the solution for that, all that we had to do to solve the one where you see the labels was just to count things, which was very easy. You just counted what you saw, and then to just divide, yeah, to get the parameters. Okay.
I think it's not found again.
Oh really? Sorry, but probably okay.
I was able to download it.
You were.
Yeah.
I think if you try again, it might work because somebody's already downloaded it. So, okay.
Okay.
Is there a better?
Loading.
Yeah. Sorry. Okay. I will share some data after the lecture today for tomorrow, so you guys can all download it at home, because it doesn't really work here.
Are we going to have any tests for this course?
Yes, since we're running out of time, you can do this for homework. So the hidden coins example. Basically, I'm sorry, this is really hard to read, but I can't change the terminal very easily. Where is it? Okay. So this has two methods. Okay. This method here. You have to compute the probability of the red coin given the data. Okay? So this is where you have to use Bayes' rule. You're given some samples, you're given the current probabilities. Okay? So these are the current parameters. So you know the probability that it's red, you know the probability of head. This is the best guess so far. And you have some samples. And for each sample, you need to compute the probability of it being red. Okay? You don't see it, but you need to compute the probability. That is just using Bayes' rule. Okay? Then once you've done that, you need to collect the statistics. So the statistics are basically you're weighting your heads and tails by a probability now. Yeah. So rather than just counting in the previous version, if this was red, we counted 3 red tails and 1 red head. But now maybe we have like 50% red, 50% blue, so we count it as 3 times 0.5 red, okay, tails. Okay, so you basically get these counts. So it's exactly the same. It's exactly the same problem. Okay, exactly the same problem. It's just that your labels are fractional rather than 1 or 0. Okay? Okay. So let me just show you how this works since it's late. Since it's late. Okay. Oh, where is it? Okay. Hopefully I have a solution here. No. What's over that? Probably I need to change these names. Okay. So the two different scripts use each other so as not to repeat things. So let's say I say a red coin is half the time, and I'll say the probability of a red coin is very high. The probability of heads is very high for red and very low for blue. And I'll flip 100 coins and I'll flip them each 5 times. So it's not many times. I'm not. Okay. Okay, so what did we get at the end? What it did is it re-estimated it many times. And at the end, it was pretty close, actually. It was pretty close, yeah? So if you did it, I mean, this is an easy one, but if you flip, like, say, let's flip 50 ones and flip them 10 times. And yeah, I guess it's about the same. So what you can see here is that this is the actual parameter I chose, and this is what it actually estimates. And what it's doing is each time it's computing the average log likelihood. So it's averaging the likelihood over the posterior distribution. So it's not exactly the same as the likelihood, but it's related to the likelihood. It's the average likelihood when you sum over the missing data. And what you can see, and this is the best way to check if you have a good implementation, is that each iteration, the expected log likelihood should increase. Okay? In fact, here, it's... Well, did it?
It's decreasing.
Is it?
It increases.
It's increasing. It's minus. Yeah, it's minus. Yeah, so it's increasing. So it's iterative, and every time it's guaranteed not to decrease. So it may stay the same, in which case it's converged. Okay, it may take a very long time to converge, but this is a very simple problem with just a few parameters, so it usually converges quite quickly. Okay, if you did it randomly, restarted it multiple times, you could easily get different solutions. Yeah. Okay, so what you can see from running this script is how you can. So I don't want to. Okay, we don't have lots of time. So we're interested in understanding the parameters of a model. So in our real application, which is machine translation, we're interested in knowing the parameters of word-to-word translation parameters. What's the probability of the word dog if I see the Russian word sabaka? Okay, that's the parameter I'm interested in. Okay, that parameter is just like one of these parameters here. It's just like the parameter probability of heads given red. There's no difference, really. The only difference is that there's only 2 possibilities here, and there's hundreds or thousands or millions of possibilities for translation. Okay? In order to estimate that, here we try to infer which source, what was the source of the data? Yeah? Was it the red source or was it the blue source? In the word alignments, we have a sentence which maybe says, I don't know, Balshaya Sabaka, and we have big dog. We need to understand when we see the word dog, is it because of the word Balshaya or because of the word Sabaka? Okay? When we don't know, at first we really don't know. So all we do is we guess some parameters and we re-estimate. Okay? And the point is exactly this algorithm. There's no difference with this algorithm and that one. Okay? The difference is the number of parameters. Okay? Okay, so what I'm going to do, because it's taken longer than I thought, I wanted to go to to actually do the word alignment as well today. The word alignment itself requires downloading 10 megabytes, so I don't want to. I don't want to try. I'm really sorry, but what I want to do is for the rest of this evening, if you have any questions, please try to make this work. Please try to make this work. If you can make this work, that's great. Okay. When you run it, it will fail, and it will say where it's failing, and I'm here to ask questions for. And then tomorrow, we will try the real thing, which is using parallel data. And please, I will email this when I get home this evening. Please download it before you come, okay? Because it's quite a lot of data. And then you will use parallel data, and you will see how the word alignment works, okay? And it's exactly this algorithm, okay? So.
Can you put the code in a GitHub repository?
I could, but I mean, it's just, yeah, I could actually.
Like not right now.
Yeah, no, sure. Yeah, I should have done that. I didn't really. Usually we have a wiki at Shad, and I just put it all on there. But okay, so now is your chance to implement the expectation-maximization algorithm, and the slides have a lot more information than I got through today, yeah. Yeah? Okay. Okay. I guess I won't do that, yeah. So the first thing to do when you do the EM algorithm is to write down this. Write down Bayes' rule. Even though Bayes' rule is simple and everybody knows it, actually, this is the thing which everybody gets wrong. Yeah. So write down this, okay? Yeah. So it's just this. Yeah.
Take as the initial parameters.
So as long as they're different, then it's fine. Whatever you choose, something random is fine. Actually, I don't know what this thing. It's probably already doing it randomly for you. What is it doing? How is it started? Wait a sec. I guess I did something to.
Well, there is something on line 42 of Hidden Coins example.
Oh yeah.
I think.
Yeah, it should.
Generate n sample size n.
Oh yeah.
42 and 40.
So you're asking where? Basically, the question is where.
It says estimate proper point R is 0.5, crop head R is 0.51.
Ah, yeah. Sorry. So this is my random initialization. This is fine. I mean, it doesn't matter as long as they're not the same. If you made them the same, then you'd have to break the symmetry later. So if you make the probability a half for each, and you make each have the same probability for heads, then that will never change. You just try it. If you change,
Seems.
Yeah, it won't. Yeah, because how can it distinguish? Everything's equally blue and equally red. There's no way for it to distinguish. Yeah. So there was a question here. this is impossible to read, but when I initialize the parameters, just a random guess, I just chose some numbers which are different. If these were all, if I chose them, if I estimated them to start with as 0.5 for everything, then the parameters would change, but I think they would be the same. I think you would end up with every sample was 50% probability of being red and 50% of being blue. And then your parameters would be updated. These probabilities would change, but they would be they would stay the same as each other. Okay? So when you initialize, you do it randomly. Yeah. So, okay.
Can you bring back this slide with the formulas?
Yeah, sure. I'm not sure if I have the important formulas on the slide, to be honest, but this thing, yeah? So this is what you want to estimate this each time, yeah? Okay, let's do it here. Come on. I know. Okay, so this thing here is the thing, the posterior you have to estimate, yeah? We know the probability of red. We have an estimate of it, yeah? This isn't the real, this is just a parameter. We have the probability of, and this is at time t. So at time t, given red, and we also have the probability of head given blue, okay? So can somebody tell me, somebody help me write this down. What's the probability of red given head, tail, head? What's that? Huh? Probability of R, okay, yeah.
Multiply probability of HTH R.
The flip probability is the HTH given R.
Yeah, yeah.
Okay, okay, but what's that? Okay, we'll do it in a second. Well, but what is the probability of HTH? Yeah.
That's
Yeah, yeah. Yeah, it's a product. It is product because they're independent, yeah?
estimation that's the probability of what heads squared times y minus heads.
Yeah. So let me do it in two steps because just to be clear, for people about this, this pen's not working. So just to write it down firstly is the probability of R, and it's the probability of heads given R, probability of tails given R, probability of head given R, okay? Divided by what? What's it divided by? So this thing here, this is just the probability of heads, tails, heads given R. But, so it's probably impossible to read, isn't it?
Yeah, it's the same thing again plus.
So what's at the bottom?
The same thing again plus the probability of the complementary band.
Yeah.
That is.
Yeah. So yeah, I'm sorry. I mean, this isn't very clear what I've written, but let me write it nicer. So it's the probability of heads, tails, heads given R. Okay, and then on the bottom we should have all of this, which means that we need to take the joint and sum over that. So it's the probability of R and the probability of heads, tails, heads given R, same as the top, plus the probability of blue and the probability of head, tails, head given blue. Okay? Okay? And then this thing is a parameter. The probability of R we know, it's the probability at time t of R. Well, that's a parameter. Oh, sorry, I'm awful at writing on these things. Let's call that, yeah, probability of R. This thing here, the head, tail, and head given R are all independent, given that it's red. They're independent, okay? Which means you can write it as a product. Probability of heads is this. Probability of tails is 1 minus the probability of heads. Oh, sorry, I'm writing this wrong. It should be red. Oh, God. And then probability of heads again, which we could just have done as squared, but let's keep it. Okay? Now, this is the same as this, So this is going to be the same down here. I won't write it again. And this thing here is just going to be, 1 minus the probability of reds. And then 1 minus, and then the probability of, head given blue, etc. Like that, okay? So I'm not sure how easy that is to read. It probably is impossible to read further back, but it's basically you just use the independence assumptions you can make, okay? Okay. But this, and then you know what's the probability of R given all this data, and this is using Bayes' rule. So everybody knows Bayes' rule, but sometimes people find it a little bit more difficult to write down Bayes' rule in a specific model, and that's what you need to do here. Okay. What's wrong?
Yeah, I thought it was like basic Bayes formula, so at the bottom it should be the probability of HTH.
It should be. That's exactly what it is. So, okay, so you're debating. Yes, so, yeah. Good question. The guys at the front aren't scared to ask questions. But so, the question was, what's the... Bayes' rule is obviously, should be like probability of R. The most simple way to do this is like HTH given R, and then divided by the probability of HTH. But then the question is, what's the probability of HTH? We don't have any parameters here which tell you the probability of HTH. Okay, what is it? Where's that from? Yeah, we can. Not estimate, we can compute it. Yeah. Ah, you mean just count the number of times we see HTH? Wait a second. So, but we don't have any parameters. All the parameters we have these are the three things that we know. We only know these three things. We know the probability of R, we know the probability of heads given R, we know the probability of heads given blue. We don't have any parameter that tells us the probability of any heads or tails without the things, yeah? There's a way to do it though. Yeah? What do we do? From the existing sample. So what does that mean? So you've got, so we've got maybe 10 different examples, each with 3 observations, and we just count. I'm not sure that's going to be right. There's a more obvious, well, more obvious, but there's a I can't remember how you say it in Russian, but you know what marginal probability is? If you have the if I know the probability of A and B, and I want to compute the probability of A, what do I do? How do I get this from this? Let's say they're both binary variables. How do I compute the probability of A from probability of A and B? I have a table with 4 different values for all the different values for A and B. I just want to know the probability of A. I don't care about B. What do I do? Oh, come on, guys. What's it equal to? Equal to the different values for B, the probability of A, comma B, yeah? 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 So you just sum over the different values, yeah?
Yeah.
Yeah?
Sum of different probabilities when we put all the variants of B.
Exactly, yeah. So if I know what, let me think, So if I know the probability, if I have some statistics like the probability of somebody's age and if they like ice cream, okay, for 3 different age brackets, and yes or no for ice cream. And I don't care about the age, I just want to know about if they like ice cream or not. I just add together all the different probabilities for liking ice cream, yeah? Yeah. So here, what you do to get this is you do the same thing. This thing, the marginal probability is equal to the probability of blue and HTH plus the probability of red and HTH. Yeah? Yeah? So it's these things. This thing here was the thing you already wrote here. This thing here is the complement, kind of. So that's how you get the bottom part, okay? Okay? This is the thing. So, yeah. Oops, too late. Okay. Yeah. So, yeah, this is the difference between, I guess, just the mathematical application of Bayes' rule and just when you need to use it in statistics. So, it's, I know it looks messy, but it's not difficult. I know you all know this.
I have a stupid question.
Yes?
Where is the theta on the right-hand side of the equation at the bottom?
Where is the theta?
Yeah, we're taking R max over theta.
Yes.
Which is not on the right-hand side.
Well, no, it's the parameters of the model. So each of those, you're setting theta in. Where's my pen go? Where's my? Oh yeah. So you're choosing this model here has some parameters, yeah, which are called theta. Okay, they're these parameters here.
We estimated the previous step.
Yes, we estimated the previous step is theta t. Okay, and we estimated, given those parameters at theta t, we estimated the distribution over the hidden variable. Yeah, using the old value for theta t. Given that, we then want to maximize all of this with respect to theta, which we're going to call theta t plus 1. Okay? So each step, it's iteratively. Where is it? It's put on the next page. So, yeah. So this is the iteration. E step, compute this thing, which is what we're doing here. Compute the probability of the hidden variable. It's our best guess, basically. Then update the parameters theta t to maximize the log likelihood. Okay, so it's all theta. The parameters are all theta. I just give them an index so that we can be clear that they change each time. Yeah. So sorry if it's a bit messy.
Yeah, we use the previously estimated parameters at one point where we calculate the coefficients.
We use the previously estimated parameters here where we calculate this thing.
Yes.
Then we stop and we pretend that those things are basically like counts of labels.
Yes.
And then we look at the data again and we say, now we have these counts and these labels and we want to get the maximum likelihood estimates for the parameters pretending that these were real counts. And you'll get a new value for theta. Then you get a new value for the z, then a new value for theta, and this will iterate until it converges. So that's why there's 2 steps to it. Yeah? Yeah? So I think the best way to understand it is just to implement it, because when you implement it, it's very, very simple. It's really, really simple. It's much simpler than it looks here. Okay.
iterating. That's нужно.
So which version of Bayes are you used to? Using like the joint probability? There's many different ways to write Bayes, but it's just different ways to write the conditional distribution, yeah? What's the version of Bayes that you prefer? This one like this? This one here?
The one with the extended denominator.
Okay. I mean, the reason we expand the denominator is because then we can write it in terms of the parameters that we know, okay? Mathematically, you can write this, that's fine, and that's simpler, but we don't know this, and we can't really just estimate it without thingy, yeah? Okay. Now, we're running out of time, so I don't want to keep people, I'm not going to go just yet, but, and I know it's late on Saturday night, so if you have a chance, have a look at this. I'm sorry that we didn't finish the main thing, which is the word alignment. I promise we do that first thing on tomorrow. So for those of you who are coming tomorrow, you will do word alignment with real parallel data, and you will see how the algorithm gradually learns to work out which word is responsible for which word in the other language. Okay? So at the beginning, every word in the English and every word in the French, say, seem like they're related to each other, and then gradually the probabilities of Z, they start to become much closer to 1. And then you see that the dog is Sabaka and Bolshaya is big and these kind of things. Okay?